Microsoft just introduced Majorana 1, the world's first quantum chip powered by a new topological core architecture that it expects will realize quantum computers capable of solving meaningful industrial-scale problems in years, not decades. It leverages the world's first topoconductor, a breakthrough type of material which can observe and control Majorana particles to produce more reliable and scalable qubits, which are the building blocks for quantum computers. In the same way that the invention of semiconductors made today's smartphones, computers and electronics possible, topoconductors and the new type of chip they enable offer a path to developing quantum systems that can scale to 1,000,000 qubits and are capable of tackling the most complex industrial and societal problems, Microsoft said. We took a step back and said, okay, let's invent the transistor for the quantum age. What properties does it need to have? Said Chetan Nayak, Microsoft Technical Fellow. And that's really how we got here. It's the particular combination, the quality and the important details in our new materials stack that have enabled a new kind of qubit and ultimately our entire architecture. This new architecture used to develop the Majorana 1 processor offers a clear path to fit 1,000,000 qubits on a single chip that can fit in the palm of one's hand, Microsoft said. This is a needed threshold for quantum computers to deliver transformative, real-world solutions, such as breaking down microplastics into harmless byproducts or inventing self-healing materials for construction, manufacturing, or healthcare. All the world's current computers operating together can't do what a 1,000,000 qubit quantum computer will be able to do. The topoconductor, or topological superconductor, is a special category of material that can create an entirely new state of matter, not a solid, liquid, or gas, but a topological state. This is harnessed to produce a more stable qubit that is fast, small, and can be digitally controlled, without the trade-offs required by current alternatives. This breakthrough required developing an entirely new material stack made of indium arsenide and aluminum, much of which Microsoft designed and fabricated atom by atom. The goal was to coax new quantum particles called Majoranas into existence and take advantage of their unique properties to reach the next horizon of quantum computing. The quantum world operates according to the laws of quantum mechanics, which are not the same laws of physics that govern the world we see. The particles are called qubits or quantum bits, analogous to the bits or ones and zeros that computers now use. Qubits are finicky and highly susceptible to perturbations and errors that come from their environment, which cause them to fall apart and information to be lost. Their state can also be affected by measurement, a problem because measuring is essential for computing. An inherent challenge is developing a qubit that can be measured and controlled, while offering protection from environmental noise that corrupts them. Qubits can be created in different ways, each with advantages and disadvantages. Nearly 20 years ago, Microsoft decided to pursue a unique approach, developing topological qubits, which it believed would offer more stable qubits requiring less error correction, thereby unlocking speed, size, and controllability advantages. The approach posed a steep learning curve, requiring uncharted scientific and engineering breakthroughs, but also the most promising path to creating scalable and controllable qubits capable of doing commercially valuable work. Microsoft's topological qubit architecture has aluminum nanowires joined together to form an H. Each H has 4 controllable Majoranas and makes 1 qubit. These HS can be connected to and laid out across the chip like so many tiles. It's complex in that we had to show a new state of matter to get there, but after that, it's fairly simple. Tiles out. You have this much simpler architecture that promises a much faster path to scale. The quantum chip doesn't work alone. It exists in an ecosystem with control logic, a dilution refrigerator that keeps qubits at temperatures much colder than outer space, and a software stack that can integrate with AI and classical computers. All those pieces exist, built, or modified entirely in-house. To be clear, continuing to refine those processes and getting all the elements to work together at accelerated scale will require more years of engineering work. But many difficult scientific and engineering challenges have now been met, Microsoft said. Getting the material stack right to produce a topological state of matter was one of the hardest parts. Instead of silicon, Microsoft's topoconductor is made of indium arsenide, a material currently used in such applications as infrared detectors, and which has special properties. The semiconductor is married with superconductivity, thanks to extreme cold, to make a hybrid. Ironically, it's also why we need a quantum computer, because understanding these materials is incredibly hard. With a scaled quantum computer, we will be able to predict materials with even better properties for building the next generation of quantum computers beyond scale. Make sure to like, comment, and subscribe